So now we're going to take two of our values that we just talked about, mass, which is the amount of matter in an object, and volume is the space it takes up. So mass and volume, we're going to take their ratio. Well, that's called density, and density is actually going to be constant at the same temperature. Now, why is that? Let's think about something we know, like water. So anything less than 0, so let's say maybe something like -10 degrees. So -10 degrees Celsius, we know that water is a solid. Let's make a little ice cube here. So this is solid water. But if we add heat, it becomes liquid water. Now, liquid water is going to take the shape of its container, but if we continue to add heat, and sometimes, just so you know, the symbol for that is a triangle, if we add heat, it becomes all these little droplets of water vapor, or a gas. And gases expand to fill the entire room. So we know that it's going to take up more space the more heat that we have. So if we look at our equation, try to make some space here. If we look at our equation, and we know that this is going to stay the same, so a number that stays the same over a number that gets larger, what happens to that fraction? Well, 1 over 2, 1 over 4, so 0.5, 0.25, right? So as we go up in temperature, the volume is going to increase, making density go down. Now the opposite will happen, so I can write that if you want. This is just some concepts about density that realistically make sense if we look at the equation, but just some ways of thinking about it. So if temperature increases, what happens to density? So mass stays the same over a number that gets larger. So that means density would go down. But if we go this way and we remove heat, that number on the top stays the same. Again, but the number on the bottom, what happens now? It's going to get smaller. It's going to go closer together. So gets smaller. That means density is going to increase. So when we look at density, it's just a ratio of the amount of matter in a substance and how much space that substance takes up. And at the same temperature, that's going to be constant. Now, density is generally in grams per milliliter, grams per centimeter cubed. You can have also grams per liter for gases, but typically these are the units that we use for density. Now, some people who don't really care for algebra like to use the triangle. I will tell you, I notoriously forget how to draw the triangle, but when you do draw the triangle, so mass, density, volume, you're just covering up what you're looking for. So let's see if I can do that with the pen. If I cover up what I'm looking for, so if I'm looking for density, it would be mass divided by volume. If I'm looking for volume, it would be mass divided by density. And if I'm looking for mass, it would be density times volume. So you cover up whichever one you're looking for, and that helps you to do the algebra. But honestly, this is very simplistic algebra. So at this point, if you're struggling to solve this equation for each variable, we really need to get you in and get you some help with your algebra before we move too much further forward. So let's go density is equal to mass divided by volume. If I want to get the volume off the bottom here, I need to multiply both sides by V over 1, the inverse fraction. So those cross out, and I get volume times density is equal to mass. Now, starting again with density is equal to mass divided by volume. If I want to solve this for, let's see, we have it solved for density here. We have it solved for mass. Let's solve it for volume. To solve for volume, we're going to get rid of that V on the bottom again by multiplying both sides by V over 1. So now we have volume times density is equal to mass. We're going to divide both sides by density and get volume is equal to mass divided by density. So pretty simplistic algebra, but this is our first step into it. So if it's been a while for you, let's make sure you review it and get some help if you need it. Let's try it. The density of ethanol is 0.789 grams per cubic centimeter. If you have 50 grams, what is its volume? So density, mass, and volume are our three variables. We are given the density is 0.789 grams per centimeter cubed. Saying you have 50 grams, well, we all know grams is a mass unit because we just studied that, and we would like to know what is the volume. Density is equal to mass divided by volume, so I'm going to be looking for volume. I multiply both sides by V over 1. I get volume times density is equal to mass, and then I again divide both sides by D, and I get volume is equal to mass divided by density. And I know I started using a large D here. It doesn't really matter, to be honest. So our equation is going to be 50 grams divided by 0.789 grams per centimeter cubed. Now this is a great time to talk about units. Remember those terms, numerator and denominator and all of those fun terms? We need to talk about those. But first, I want to ask you, this number, the answer to this here, should this go up or down? Well, if you remember way back when, you probably learned a little bit about this, but this is a number less than 1. So if we're dividing by a number less than 1, our number should increase. And this comes out to 63.371356147. Now, what's our unit? Grams in the numerator, in the top, are going to cancel with these grams in the bottom. And now essentially we have 1 over centimeters cubed. So this number is in the denominator, which actually means it's in the numerator. So our answer here should be a volume unit, and it is. It comes out to be centimeters cubed. Now, we haven't talked about the rules of significant figures yet, but I am going to tell you that in multiplication and division, you look at the total number of significant figures here. That is 3 significant figures. And I look here, it's 3 significant figures. 1, 2, 3. I look 1 to the right, which helps me round. 7 is greater than 5, so I'm going to round this number up. So if my final answer is going to be 63.4 centimeters cubed, I have a number, I have a unit. but now I need a label. So what is my label? What do I have 63.4 centimeters cubed of? Ethanol. So this is my final full credit answer. Erase that because I have it here too if you'd like to see it in type. Given the density of gold is 19.3 grams per centimeter cubed, calculate the volume in centimeters cubed of a gold nugget with a mass of 5.98 grams. I would like you to please pause the video. So pause the video, try your best to get the right answer, and then we're going to go through it. No, really. Seriously, pause it. And I'm going to start working on it, and you can hit play once you're done. Density is 19.3 grams per centimeter cubed. Mass is 5.98 grams. So what do we need to do here? We need to say, well, what are we solving for? Volume again. Well, hopefully you remember from the last slide that volume is equal to, well, what if we don't? Volume is equal to, I can't remember. Well, we can actually use this density as a conversion factor, and we can convert by starting with the mass, 5.98 grams, and there are 19.3 grams for every 1 centimeter cubed of this substance that we have, this gold nugget. So 5.98 divided by 19.3 gives us 0.3098445596 and centimeters cubed. So this is called dimensional analysis. This is my conversion factor. And this is the number given in the equation. So I take this, I do the math. Now I want to look at my significant figures. I have 3 sig figs here. I have 3 sig figs here. So 1, 2, 3 in my answer. This means I'm going to round this one up. So this would be 0.310 centimeters cubed of gold. Good. Let's try another one. Let me erase this here. So let's try another one. Given that 25 milliliters of mercury has a mass of 340 grams, so density, mass, volume. So 25 milliliters of mercury has a mass of 340 grams. Calculate the density. Density is equal to mass divided by volume, or in this case, 340 grams divided by 25 milliliters. So when we do that math, what are we going to get? So 340 divided by 25 is 13.6. And this is 4 sig figs, and this is 2 sig figs. But I think it's actually more than that because it says 25.0, and I forgot to write the 0.0. So 25.0 makes that, instead of 2, it makes it 3 sig figs. So we get to keep the 13.6, and the units are going to be grams per milliliter here. Part B says the mass of the solution is 120 milliliters of mercury. Excuse me. It says find the mass. So find the grams of 120 milliliters of mercury. So we're going to have to get some other information, and the information we're going to need is right here. This is the density of our mercury. So density is equal to mass divided by volume. We have our density here. It's 13.6. grams per milliliter. All right, we have 120 milliliters, so we're just going to divide those. So we get 13.6 but we don't actually divide them, do we? I guess I was getting a little tired there for a minute. We actually need to multiply them. So this is a good time to check your math, especially if you're getting tired like I am right now. We want to make sure that we look at this. I said divide, but I meant that because I was actually writing the division symbol. But in order to solve for mass, we need to divide that. And why can we use the 13.6 grams per milliliter? Because if we're at the same temperature, density is going to be constant. So here we're going to have mass is equal to 13.6 grams per milliliter times 120 milliliters. The milliliters cancel. We're going to be left in grams, so that's good for a mass unit. So we take that into our handy dandy calculator and we get 1,632 grams. Looking at sig figs, we have 3 sig figs here and we have 4 here. So we can have 3 in our answer. 1, 2, 3. We look 1 to the right, so we round up. So our final answer would be 1,630 grams of mercury. And Hg is the chemical symbol for mercury. I keep forgetting to erase the ink before I click through. So those are the answers to the density equations. So you should practice that, make sure that you can answer and solve for all variables. And if you have questions, let me know. Next up is accuracy and precision. So, a lot of people use these terms, but have you used them accurately? So accurately is how close to the measurement, how close the measurement is to the true value. So if we were to draw a dartboard, yep, that's a circle. And we have, or actually like a target, maybe for target practice, and we have this target, all of us usually understand that we're trying to hit the bullseye. But what if we don't always hit the bullseye? What if we come out here a little bit? What does it mean if we're not always on the bullseye? So we need to tell people how good is our instrumentation. So accuracy is how close we are to the center of the bullseye, the true value. How close are we to being dead on center, or whatever the target may be? Precision is how close multiple measurements are to one another. So if we were to look at these 2 dots, they have relatively good precision. If we were to look at this group out here of dots, we would say they have relatively good precision. But if we put these together, they don't have relatively good precision. The dots are very spread out. So sometimes drawing a picture really helps. One thing that used to help people is the trash can game. So I want you to pause the video and try to describe the precision and accuracy of each of these pictures. So you can describe it as accurate, precise, neither, or both. So in this case, the first one, well, believe it or not, folks, I don't know who you live with, but in a sense, the goal is actually to get the trash into the trash can. So the first one would be both accurate and precise. Over here, we see that the paper balls are all very close together, but none of them made it in the trash can. So these are precise because they're close to each other, but not accurate because they're not in the trash can. And this one, these are not close together at all. They're spread out and none of them are in the trash can. So this is neither accurate nor precise. So since they're all far around it and you can't get, they're not considered to be precise. So it's very difficult to be accurate but not precise. So it's hard to determine if something is accurate but not precise. Have you guys heard the old thing, it works in horseshoes and hand grenades? Almost works in horseshoes and hand grenades because, I don't know, for horseshoes they give you a point, but for hand grenades, if you almost make the target, you're probably still going to blow up most of your target. So almost is still good. But if you work in a lab, they're going to give you these things called reporting limits. So you're going to constantly have to be standardizing your instrumentation. You're going to take it against usually NIST standards. NIST, it stands for National Institute of Standards and Technology. You can buy standards from them or you can make your own and standardize them against them. That's usually what companies want to do because it saves money. Buying a standard is expensive. Making your own and using a standard to standardize it is going to be a lot cheaper. So the company is probably going to want you to make your own. So while you can be accurate but not precise, it's more difficult to explain. You have to say, well, yeah, they were all pretty close, but they weren't close enough for what you wanted. So when I worked for Airgas, we used to have these limits that we had to stay within. There was a 1% blend tolerance. Well, on something that's, basically all helium, that's not so bad. Air being 21% oxygen and balance nitrogen, those wouldn't be too hard to hit the mark. But if you're trying to do something else that has to be much smaller quantities, it can be very difficult to hit the mark. So your company will have what are called reporting limits. Now this is something we might see in chemistry is a set of data. So we have a set of data here from student A, here from student B, and here from student C. We are asking them to take the mass of an aspirin tablet. We have determined the aspirin tablet to be 0.370 grams. Student A got 0.335, 0.331, 0.333. Student 2, 0.375, B, 0.375, and D, I say B. Sorry, B got 0.375, 0.375, and 0.338. Student C got 0.369, 0.373, and 0.371. So looking at these individual results can be a little bit more difficult than something like the trash can where we had a picture. So don't be afraid to draw a picture. So sometimes the bullseye analogy works really well for people, or what we do in science is graphing, right? So these are the student A results, and this is the true value. These are student B's results, and this is the true value, and this is student C's results. Looking at these, it's very obvious that this one is going to be both accurate and precise. This one, they're definitely not precise, but they could be considered accurate. And this one over here, this is so much different. So they have all their values down here. They're precise, but not accurate. So A would be precise, but not accurate. B would be neither, and C would be both. All right. That's it for this one. We'll see you on the next one.